Welcome to Lesson 8 of Module 4, the final video in the Module 4 series. We're going to start with our do now. What do you know about Albert Einstein? And do you remember anything about nuclear energy? So the reason why I got you to think about Albert Einstein and nuclear energy is because we're still answering our final inquiry question of how are theories and laws used in science, but we're going to be looking at how nuclear reactions and decay change the way in which the law of conservation of mass and energy are interpreted. So far, we've looked at how laws and theories change over time due to new evidence. But what we're looking at today is what happens when we record information that challenges what we know, and it's the only anomaly for that law. So our learning intention is to challenge standing ideas with evidence. So Einstein equation E equals mc squared. It's probably the best known equation, and it's because it has changed how scientists view energy and matter. And the equation shows that energy and matter are two forms of the same thing. And when Einstein introduced it in the early 1900s, it in fact was crazy to think that it could replace what we already know. And so the idea, though, has withstood the test of time, and more evidence has been gathered to support it, so that we now still use it today. So when we look at E equals mc squared, so it's the theory of special relativity. It's the energy and mass equivalents. And so energy and mass are equivalent and are interconvertible. And what we can see here is that the total mass of an atom is the total mass of the atom and its components. And we can see here that this is a shifting cycle. So mass defect, which is another concept we're going to look at within this law, is that the mass of the whole atom is less than the total mass of its components, and that binding energy is in fact required to completely separate the atomic nucleus into its components. So looking at this E equals mc squared in a little bit more detail. So E is for energy, m is for mass, and c is the speed of light. So what we're looking at is that the amount of energy, even in a small amount of small mass of matter, is in fact massive. So Einstein equation helps scientists to understand what happens in nuclear reactions and why in fact they produce so much energy. So when atoms split apart or when they join together, energy is released. So the splitting of atoms is called nuclear fission, while joining atoms is called nuclear fusion. So when an atom undergoes this fission or fusion in a nuclear reaction, a tiny amount of matter is lost. So what happens to the lost mass? Well, in fact, it isn't actually lost at all. In fact, it is converted to energy. And so then we ask the question, well, how much energy? And in fact, that's what E equals mc squared explains. So the change in mass is tiny, but it results in a great deal of energy. So in a nuclear reaction, mass decreases and energy increases. So what happens to the laws of conservation of mass in these nuclear reactions? Some people would ask, well, in fact, are they not conserved in nuclear reactions, and therefore do they not apply to nuclear reaction? Well, the answer is no, the laws still apply. However, it's more correct to say that the sum of the mass and energy is always conserved in a nuclear reaction, and therefore mass changes to energy, but the total amount of mass and energy combined still, in fact, remains the same. So in this case, we look at mass and energy as interchangeable. So a little bit more on the application here. So when an unstable nucleus undergoes radioactive decay, the mass is in fact lost and converted to energy when alpha or beta particles are emitted. And any excessive energy in the nucleus is released as gamma radiation. And we can see that happening here. So the mass and energy relationship, so seeing that the alpha, beta, and gamma emissions happening here. and the unification in mass and energy. So, chain nuclear reactions are an example of the unification of the laws into the mass energy equivalents. So, the amount of mass of the reactants is not equal to the mass of the products due to the fact that some of the mass is converted into energy in the forms of photons, heat, and new smaller elements. So, we see that happening here. So, the amount of heat being released here, okay, we say that these mass and energy equivalence is happening here. And then we're going to watch this video. So this explains to us 4 of Newton's miracles, I guess, and we're looking at the 3rd and 4th in this video. And then finally, we're going to complete our last Google form that has our practice questions in it and updating our inquiry question log for how are theories and laws used in science, remembering that E equals mc squared challenges the laws of mass and the law of conservation of energy, is the idea that there is a mass energy equivalence. Good luck for your Year 11 yearly exam.